The problem is, in order to explain why it's sort of a very deep and interesting problem, I have to go through some number theory, some real number theory, so to say. So let's consider a simpler problem, which is somehow has the same flavor, namely the problem of dividing a circle into n equal parts. So if I want to divide a circle into 7 equal parts, the idea is that all these segments should have the same length. It will look something like this, I hope. And the question is how you can do that. The first thing that strikes you when you look at this is, of course, that one can generate these vertices here with a group. So there will be a little group generating these things, right? In this case, 7 is a cyclic group. And the second thing that strikes you is that the thing actually has a bit of an additional symmetry. You can make little turns here, and that leads to a slightly bigger symmetry group called the dihedral group, etc., etc. These things have their counterparts here. In principle, it should have been done in such a way that this came up but okay, it didn't work. Pardon?
It's easier to make up.
I will try to do as well as I can, and we'll see what happens. So this symmetry part has immediate counterpart here. So there was a conjecture by the person who first brought up this person, Gerhard Sauner. He made the following conjecture. Seeks exist for any dimension, and they are orbits of a group which he identified. It's called the discrete Vial Heisenberg group. 3 times louder. You want me to write larger?
Yes.
Oh.
Larger font.
And larger font and louder and larger and funnier, is it? Okay, so Sauner's conjecture was that these things, the maximal equiangular tight frames, always exist, and that they orbit under the Vial Heisenberg group. This is so to say a known group. It's this is bigger. It's a central extension. It's a well-known group. It's a good group. It's a central extension of the product of 2 cyclic groups. It's a good group in the sense that it's a very useful group, both in quantum mechanics and in signal processing. He also made conjectures about symmetries of the seeks. I'm not going to go through the details. It's an interesting thing, but the symmetries come from a discrete symplectic group. So he made this conjecture. Once you have such a conjecture that these things are generated from a group, they become comparatively easy to search for numerically. And this has been pursued. So numerically, people have searched for such things. And the results so far, they exist, and they obey all the conjectures made by Sauner for d smaller than, it's, I think 181 is the state of the art. All these calculations are done by a person called Andrew Scott. I should say that in some higher dimensions there are solutions too. The world record, you can see that this is a business where we like to keep track of records, is dimension 2208, where Andrew Scott found the solution. So that's good. But then one wants the exact solutions for these things. That's trivial, even if dimension is 2. It's easy if the dimension is 3. The German mathematician Otto Hesse actually found the solution in dimension 3 already in 1844, so before all these things, as torsion points of an elliptic curve. But that's a very easy case. When d is larger than 3, it's a hard problem to find these things exactly. So let's go back and see what these points are exactly. So we introduce the usual coordinates, and we put this point here at 1, 0. And then the question is, where should we put this point? And here, the x value, and here I have to look in my notes. The precise value here for the x coordinate of this point is 1 over 6 times the cube root of 7 plus 21 square root of minus 3 divided by 2 plus the cube root of, this is for the 7 gone, plus, minus 21 square root of minus 3 divided by 2 minus 1. And then you put the y coordinate at the square root of 1 minus x squared, and you're done. So this is what an exact solution for this problem looks like. And it's not, oh, you're here. Oh, good. I should convey my greetings from my wife. Jurek had a very interesting interaction with my wife, which, however, is not the subject of this talk. But you affected her life at one point in a significant way. So my best regards from her. Yeah. But this is clearly a number this is a number. And why does it look like that? It's a number that you can get by taking root extractions. This is actually a little bit surprising. Let's introduce complex coordinates. So I introduce omega is x plus iy. And so this, for this particular, omega is this particular thing then for. And then the other thing, so this is at omega, and then this thing is omega squared, etc. Now these complex values or the position of the vertices are actually the roots of a polynomial. Called a cyclotomic or circle dividing polynomial. And it's a sixth order polynomial in this case. So it's surprising that such an expression exists, because it was proved by Abel and others that polynomial equations of degree higher than 4 typically don't have such solutions. But this one has. Why is that? Well, to see why, you investigate the Galois group, permuting the roots of the polynomial. And then you see something interesting. So suppose you start with the root omega here, and you have a permutation that takes you to omega cubed. So to this corner. But then, of course, there's a consistency condition. If you take omega to omega cube, you have to take omega cubed to omega cubed cubed, omega 9. It's a 7th root of unity, so that's actually equal to omega 2. Omega 2 then, for consistency, goes to omega 6, which goes to omega 18, which is the same thing as omega 4. Omega 4 goes to omega 12, which is the same thing as omega 5, which goes to omega 15, which is the same thing as omega. So you see that the group that permutes the roots of this polynomial while leaving the coefficients fixed is a cyclic group. Or the important thing is that it's an abelian. It's a cyclic group, but in particular it's an abelian group. And Galois proved that whenever this group permuting the roots of a given polynomial is abelian, you can get by with somewhat less. then you can find solutions in terms of root extractions. So this is the beginning of the number theory. But then there is something here which is waiting in the wings. This is really hard. But let me just write here. This is the observation that makes this problem trivial in a sense. You introduce a transcendental function, a function of x, which is e to the 2 pi I over x. And then you evaluate this function at rational values of x. And then you get all these roots. So the thing that makes these numbers simple and useful is the fact that you introduce this transcendental function here. And here I should just like to draw your attention to the fact that this also shows that this is an extremely interesting and important problem. Because our whole modern civilization basically would collapse if we didn't have things like the exponential and trigonometric functions. And these things sort of come out of this problem. So it's an important problem, and it's solved in this way. And yeah, so this is a crash course in number theory, which is takes a few more minutes. What I just defined for you were the cyclotomic or circle dividing number fields. Which is what you get if you start from the rational numbers and you add a root of the cyclotomic polynomial. You can do this, I did it for n equals 7, but you can do it for any n, right? So you get a number field by extending the rational numbers in this way. And they are all abelian extensions of the rational numbers, because the Galois group of the defining polynomial is abelian. Now, Kronecker and Weber proved a very important theorem here, which is that every number field which is abelian over Q in this sense is a subfield of a cyclotomic field for some choice of n there, for some conductor, as we say. And the cyclotomic fields are completely understood in terms of a transcendental function. Then Kronecker had a dream. He wanted to repeat this construction for every abelian extension. So he starts with a different number field. He starts out by laying out the number field you get from the rational numbers by adding the square root of a negative integer. This could be -1, in which case you get what's called the Gaussian numbers. And his dream was that there should be a similar theory. You should be able to identify some special fields here called ray class fields that would be completely understandable in terms of suitable rational transcendental functions, such that every number field of this kind sits in one of those. He sort of identified those. They were elliptic and modular functions now rather than just exponentials. But it's a similar story. And by 1900, it was already clear, although the details were not completely in place, that Kronecker's dream would be realized very soon. So then Hilbert, when he formulated his problems for the 20th century, he had one. Hilbert was enormously impressed by this. One of his problems was repeat this thing for arbitrary starting points or base fields. So you should consider abelian extensions over basically arbitrary base fields, and you should have a similar theory in terms of transcendental functions that would give their generators, so you'd be able to understand that. First open case that mathematicians immediately set to work with is if you choose the base field to be, not as Kronecker was choosing, the square root of a negative integer, but the square root of a positive integer. That sounds like a rather simple variation on this theme, but it's not. It turned out that the 20th century was too short for this, so mathematicians still haven't solved this problem. They don't understand general abelian extensions over this base field. What they do is, let me just tell you that first part is solved. There are what's called ray class fields, which have been completely classified. And which are characterized by choosing an integer called the conductor again. So it's known that every abelian extension over this thing is a subfield of one of these ray class fields with conductors that have been classified by mathematicians. But no formula for the numbers that generate these fields is known. That's a slight exaggeration because there exists an interesting conjecture about them, but I slur over that. So this is an open problem. And it's sort of in a grand tradition here. And now we go back to the seek problem. So after Sauner at first didn't find anyone willing to read his thesis, and he was disappointed, and he went to Siemens, and he's now very rich. But a few people continued to work on this, and in particular, they found exact solutions for seeks using Gröbner basis techniques. It's a difficult thing, but for all dimensions d up to 16. And there was also a world record, d equals 48. This is some special dimension. This was done mostly by Marcus Grassel. There's incidentally also a record. So this is heavy computer calculations. There is also a record for the largest dimension in which anyone has done these calculations by hand. It's d equals 19. That's a very special case. This was done by Marcus Appleby. Yeah, sorry, this is not your usual thing, but now comes the clincher, so to say. So in 2016, what happened was that Marcus Appleby, Steve Flamia, Gary McConnell, who's a number theorist, and John Yard made an important observation. They looked at all these exact solutions that people had produced, mostly Marcus Grassel. They were sort of, if you look at them, They presented, of course, as text files. See if I can get this up a little bit. They presented as text files, and they're chock-full of things like this, except that the typical exact solutions takes, let's say, 6 pages of printout, fine print to present. But they're full of these things. Now, these people analyzed exactly what these numbers were that appeared in these solutions, and they found that in every known case, the numbers in the seek, in dimension d, in the dimension d seek, expressed in a natural basis determined by the group, of course, the numbers that occur in the seeks generate the ray class field with conductor D over the real quadratic field Q of B0, where this is a positive integer, just like in Hilbert's 12th problem, where D0 is the square-free part. So if you make a decomposition into primes, there should be no squares. The square-free part of d plus 1, d minus 3 for some reason. So this was our observation. And then, of course, I conjectured that this would happen in every dimension. And suddenly I find that the problem gets a completely new motivation here. Because this means this doesn't solve even this subcase of Hilbert's 12th problem, because there is no formula that gives a seek. There's no transcendental formula that gives a seek on offer. But it seems to be true that they do exactly the job which is missing from Hilbert's 12th problem. They generate, admittedly, a particular class of these ray class fields. So it certainly means that the seek existence problem and Hilbert's 12th problem is part of the same, it is closely connected. With this result in hand, once you know what number field you're looking for, then you can start converting numerical solutions into exact solutions. And if you succeed, you have a confirmation of the conjecture. This has now been done for up to D26, I think. And the world record is 1299. That's unofficial. The official world record is 323. These results are due to Marcus Grassel, again, mostly. And my personal record, if you want to know, is dimension 195. So I'm running a bit behind. And then, with maybe 3 minutes left, you looked sternly at me. Let me just try to explain what I have been trying to do for the last 3 years. So if you fix the base field, say you put 5 there, then there are actually an infinite sequence of possible conductors that obey this equation. So this gives sequences of dimensions. For instance, you can put a real quadratic field over square root of 5, and then the solutions to this equation, the square-free part here has to be kept in mind. So one possible solution is dimension 4, but then 8, 19, 48, 124, 323, 844, I think, 2208, and so on. So whenever you fix a quadratic base field, you get an infinite sequence of dimensions. And then you also get two questions. By the way, the special dimensions here, 2208, etc., have to do with the fact that if a dimension occurs high up in such a sequence, there's a fairly large symmetry group, which makes them possible to find. But anyway, we now have two questions. There's a hard one, which is, do these sequences of dimensions have anything to do with physics? I don't know any way to address this question, but I hope the answer is yes. But I think that's very difficult. Then there's a comparatively easy question, presumably, namely, can you use these sequences to produce an inductive existence proof for seeks? Namely, one would like to have an inductive proof that says that if it exists in dimension this, then it has to exist in the next dimension. Since we know 4 exists, if we had such an induction step, we would get existence proof in an infinite sequence of dimensions. That's presumably easier. I've been doing this for 3 years. I haven't done it yet. But I think still it's an easy problem, and I expect that by the time you celebrate your 70th birthday, if nobody else sneaks in there first, I will present the solution to this one. I think it's easy enough for me to solve. Thank you.
Questions?
So actually, the 6th-order polynomial that you wrote is a palindromic polynomial because the coefficients read the same from left to right. So you can halve the degree by just writing it, the equation in terms of x plus 1 over x.
That's right. It's palindromic, and this has to do with this is also why you get phase factors as solutions. Yes, yes. But that's for the cyclotomic polynomials. It's a
Some more questions? Okay. So, sorry, there is one.
Maybe just an expectation from whether sort of
whether this problem of having these 6 in the Hilbert space will help solve the mathematical problem of classifying these field extensions, or whether it's more the other way around, that the techniques that are and results that are known about the fields will help the Hilbert space situation.
That's hard to have an expectation about. I just would like to point out that mathematicians were pursuing their viewpoint for 100 years, and they're not very close to getting there. So I hope the answer is that with the kind of intuition you get, in particular from quantum information theory, you can get somewhere. That's my hope.
Your example of this regular 7-gon, part of which is visible there.
Yes, and I didn't figure out how to make it completely visible. But
it is reminiscent of a Gauss's proof that you can construct a regular 17-gon with a ruler and compass. So does anything special happen with 17 in this game?
17, so that's dimension 67, etc. No, I mean what Gauss actually proved was that if the numbers that come out by root extractions from the cyclotomic polynomials are given purely by square roots, then you can construct it in terms of ruler and compasses. If cube roots occur, you can't. So you can't do the 7-gon, but actually you can do it for the degree of the cyclotomic field that occurs in the 17-gon is 2 to the something. So that's doable, and there are 2 more cases. I don't really have much. 17, yeah. It happens that last week I was actually frenetically trying to get the lowest dimension with conductor 17 out of my computer, and I failed, but I almost did it. But the degree of that field has a factor, the ray class field has a degree which includes a factor of 11 squared, and that's sort of, no, sorry, it's not as simple as that. And in particular, it has nothing to do with Gauss. Nor is dimension 17 very simple. No.
Okay, I think it's time to thank the speaker again.